Michelle Kidwell-Gilbert, Chair of the Archaeology Committee, and I welcome all of you here to what's going to be an extraordinary event with Professor Stephen Pekar. This program was initially envisioned perhaps 10 years ago, but only last year did Professor Stephen F. Pekar agree to lecture about evidence from the equator to the poles, how climate change impacted the ancient world. His transformative talk will help us better understand the past, adapting for climate resilience while predicting more confidently the future, and hopefully avoiding the severity of ensuing disasters. Our subject is particularly timely. This September, United Nations Secretary General Antonio Guterres released Our Common Agenda, which outlines his concerns regarding a climate change. In October, the Nobel Prize in Physics was awarded for the first time to 3 research scientists who created climate models: Klaus Hasselmann, Giorgio Parisi, and Sakura Manabe. The Glasgow 2021 United Nations Climate Change Conference, also entitled the 26th session of the Conference of Parties, in November posited that irreversible damage to the Earth is imminent. Or is it? That's one of our big questions. How can our community escape the devastating threat caused by extreme weather events and rising temperatures? Innovative and sustainable solutions connected with long-term climatic trends are mandatory. However, let us first comprehend what this entails by viewing a timeline of phases, weather phenomena, cycles over seasons, interconnections between environmental disorders and fluctuations, as discerned through Dr. Stephen Pekar's discussion of, another quote, low latitude events affecting bygone societies. Witness climate change's contribution to the collapse and demise of civilizations such as Bronze Age cultures and the Maya, dated to between 800 and 900 of the Common Era. This subject was only once before broached at the Arts Club with Professor Miroslav Barta of the Czech Republic. They now have a slightly changed name, in terms of the transformation of and the formation of prehistoric Egypt. And I say it was wrong on my part not to think in terms of bringing scholars in this field. And I was trying with Steve for quite some while to get my emails and phone calls. Yet this topic is of major significance. And for that, we're so grateful as Professor Pekar cites data that the climate change currently threatening humanity's future should not be viewed as something unique just to our era. Renowned geologist Dr. Stephen Pekar, Archaeology Committee member and professor at the School of Earth and Environmental Sciences at Queens College, shares critical information garnered from his research. He participated in scientific explorations and expeditions around the world, from the tropics to Antarctica, which he visited 4 times, as well as traveled to over 60 countries on all 8 continents, including the newly named Zealandia. He is married to interdisciplinary social science scholar and public health specialist, Professor Annie Villarich, also of Queens College. Stand right there. A full partner. They say behind every great man is a great woman, and behind every great woman in this case is a great man. It's a perfect match made.
Can you believe it?
I've seen it in action. In any case, Steve, would you join us?
Sure.
And thank you.
Thank you. Well, thank you, Michelle. That was an amazing introduction. I learned things about me just now. And so I want to thank, first of all, Michelle Kidman for inviting me to the National Arts Club. It's an amazing club, and I'm just so glad that so many of you were able to get through the movie set just now. They actually stopped me, and I said, excuse me, I'm a New Yorker. I got to get to a club. And so before I begin my talk, I would first like to acknowledge the International Ocean Discovery Program, because that's the organization that allowed this expedition to happen near Antarctica, where we got this exceptional sedimentary core that spans the last 11,000 years, and it allowed me to develop climate records that we can actually have high enough resolution to teleconnect to the low latitudes. Well, I also want to thank the National Science Foundation, or acknowledge them, because they funded this project, along with my co-PI, Rob Dudmar, for Stanford University. So all the records that you see that I produced was funded by your tax dollars. Thank you very much. And so today's talk, I'm going to first introduce the International Ocean Discovery Program, because it's the coolest, I think it's the coolest science program in the world. And I'll specifically talk about the expedition that I was part of. We're in East Antarctica, in an area called Wilkes Land. And then I'm going to talk about this exceptional core, where it's a sedimentary core that looks like a tree ring from the bottom of the ocean off of East Antarctica. I've never been able to put those three nouns together in one sentence before, where it makes sense, and it does. And then I'm going to show you some of the climate records that we see from this site. And then this is the Archaeology Club. And so I will try to convince you that these high latitude climate records are teleconnecting to low latitude atmospheric systems like El Nino, La Nina, ENSO. And once I can do that, I can connect the high latitude climate records I have all the way to the collapse of the Mayan civilization. I hope to be able to convince you by the end of the talk. And then I have a couple of slides talking about the late Bronze Age, where there could be, I just started doing some research on this, on a climate connection and a possible signal coming from Antarctica. But I'm talking about civilizations that collapse because of climate change. Woo. And we're having right now in Glasgow the most important conference of our generation, okay, the COP26 on climate change. And so I would like to end talking about climate change today and how it's affecting our civilization, and how climate change today is going to be stressing our civilization, perhaps even to the breaking point. And so let me introduce the International Discovery Program. It is the most successful international earthbound science program ever. It has 26 countries that belong to it. It's been going on for about 50 years through different iterations. And with the 26 countries, it's almost like being with Captain Kirk on the Enterprise. We're all working together. There's no national posturing. And we have drill ships. This is the drill ship I was on. I'll show you that some more details in a few moments. And we can obtain sedimentary and rock cores. We can extend a pipe over 13,000 feet through the ocean, and then take cores. The record is about 2,000 meters, so that's 1,900 meters. That's about 6,000 feet below the sea floor. That's the technology we have. And we're not talking about drilling for like oil and stuff like that. We're actually getting full sedimentary cores and rocks. The goal is to try to understand our climate and oceanographic history going back about 100 million years. And what's the point of that? So we can understand our world today, because the past could be a key to our present and our future. And so this is the Journey's resolution. I've been on this ship 4 times. It's a big ship. It's a very big ship. It's almost 500 feet long. Okay? That's a lot of buses. And it's got a drilling derrick that's about a little over 200 feet tall. Right here is where the moon pool is. That's a hole in the middle of the ship. That doesn't sound good, right? But it's where we put the pipe through so we can get the sedimentary cores. So it is a drill ship. It is a drill ship. but it's also a floating science research center. It's like the Enterprise. Instead of like, you know, people from Vulcan, we have people from all around the world. So this is the night shift. Okay, we have 2 shifts, 2 12-hour shifts, so we work 12 hours a day, 7 days a week for 2 months, and we love it. And so she's from Italy, Japan, Germany, China, France, India, Queens. Talk about diversity. And so it's an amazing ship. And so we have 30 scientists broken into 2 shifts. And basically what we do is that we have expertise in just about anything we can do to the core. Okay, and so how do we get the sedimentary cores? Well, this is right here is where the moon pool is. You can't see it, it's covered right now. And what we do is we have 100-foot lengths of pipe that we screw in one at a time, and we just keep extending them through the water column. And then at the bottom is our drill bit. Okay, you're not going to find this in Home Depot. And so then we just keep extending the pipe. And so this little animation showing how we do this. So we're screwing in 100-foot pipes one at a time, extending it through the water, through thousands of feet of water, sometimes 10,000 feet. There's the drill bit at the bottom here, and it descends until it hits the bottom, starts drilling, and we get about 30 feet of core each time. At the same time, we drop down the drill string, and that captures the core and brings it up through the pipe one after another. Okay, boom, and it comes right back up. And we do this 24 hours a day, 7 days a week when we're on the drill site. And each expeditions are approximately 2 months. I'll be going back out on the ship next June, in fact. Okay, and so let's get to the expedition. Wilkes Land. Expedition 318, East Antarctica. And the original expedition was for cores from deep time, from millions to tens of millions of years ago, because that's when CO2 was significantly higher than today. However, Rob Dunbar, my co-PI, he asked and was able to get another site, which ended up being called U-1357, and this was on the shelf. So this is Antarctica here. This is the continental shelf. Here's the deep water. Here's the different sites. And here's right up maybe 20, 30 kilometers off the coastline was this core. Now this core is super unique because here's Antarctica again here. Here's the continental shelf. And you see that dark blue? That's because it's a big trough. It's a big basin. And here's a blow up showing East Antarctica here. This is pointing northwards. And that blue shows that this is a deep trough. So you can imagine the sediments, you know, are being moved slowly by currents. And when it gets over this deep water, they settle down. So we end up getting sedimentation rates. Well, first of all, we ended up recovering 170 meters of core over only the last 11,000 years. That gives us sedimentation rates of 1.7 centimeters per year. When I look at deep time sediments, we're lucky if we get 2 centimeters per 1,000 years. So we're getting almost 2 per year. And so then after that, the 30 scientists jumped in and we started taking geochemical analysis, looking at the microfossils that are in the sediments, so on and so forth. So this is the way the core looks. The core comes out, we split into 1.5 meter sections because you can't walk around with a 30-foot long core. And then we split it. One half goes to the archive, doesn't get touched, and this half here is where we can take samples and things like that. Okay, and so this is a close-up of the core. This is in centimeters here, and the light green or yellow, okay, that means there was open water. That means the sort of phytoplankton in the surface waters are just really reproducing and so on and so forth. And the darker gray layers is where there's more ice cover, so they are not reproducing as much. And so while not every dark and light layer represents a year, a season, okay, they do represent times when the sea ice was broken out, where we have open waters, and times where there's more ice across the summertime. And this core is so unique. I mean, it's continuous high sedimentation rates from near Antarctica over the entire Holocene. Wow. So Most of the little phytoplankton are called diatoms. I didn't study them. The ones that I looked at are actually called foraminiferous. And these are one-celled organisms that make the shells out of calcium carbonate. This scale here is 1/10 of a millimeter, okay? But look how beautiful this is. This foraminifera, single cell, no brain, no nervous system, and it makes shells this beautiful. Magic, okay? And so since the shell's made out of calcium carbonate, C for carbon, we can take carbon isotopes. O for oxygen, we can get oxygen isotopes. And then we can also look at the different species and so on and so forth, their abundances, and say a lot about the climate and environmental changes. And so, but before I go into the actual data, I just want to show off a little bit. Rob Dunbar did most of this. He developed the age model, and we have 87 carbon-14 dates. 87. And they're not cheap. And you can see that there's a really nice, consistent stratigraphic order for all the carbon-14. So the age uncertainty within the core is probably 20 or 30 years. But to be quite, us scientists, we like to be honest. You show off your uncertainties and you talk about your errors. So correlating from one place to the next, it could be an uncertainty maybe of a couple hundred years. But I'm going to show you some of the data when I start correlating to other records that I think it's a lot better than that. But we have to be honest, it could be a century or two. Fine. So let's talk about one of the records, and this is oxygen isotopes. And this is going for the x-axis from today back to 12,000 years ago. Don't worry about these numbers per se, and you're probably thinking, I came here for the archaeology meeting and I'm getting geochemistry. Ouch. Okay. Take-home message. Here's the take-home message. Oxygen isotopes from planktonic forams are controlled by sea surface temperatures, SSTs, sea surface temperatures, and also how much glacial melt is happening. You can always ask me why that's happening, but right now just accept it so I don't get too geeky. And so the next thing I want to point out is that we got these two lines showing 0 degrees Celsius and plus 2 degrees Celsius, and that's the envelope of where most of the oxygen isotope values are lining up. The reason why it's a little bit higher here is because the ice sheets were still melting here, and so that glacial meltwaters which changing the signal. After about 6,000 years, there's no more real ice melting. Whoops. And I got too excited. And you can see that it's all, for the most part, within that envelope except right here, okay? And so this outlier occurs between 1400 and 800 years before present. And that's where this is the first place I want to start focusing on. And so here's the oxygen isotope record just from my data set. Okay, going back to about 5,500 years ago. And you could see the oxygen isotopes and then this big outlier right here. Like I said, this is controlled by sea surface temperatures and glacial melt. Then other sets, this is carbon isotopes and planktonic forams per gram. Don't worry, there will not be any surprise quizzes at the end, okay? These are basically controlled by surface water productivity. And then finally, the last two sets is from foraminiferas that live on the sea bottom. So this is just two different groups, kept it easy, calcareous versus agglutinated, and they're basically controlled by currents and oxygen levels and other indicators from the deep sea, from the bottom. So what do I see in these records? Well, the first one is this one, okay? This big event here of warmer, this represents 2 to 3 degree sea surface temperatures warmer than the normal, okay? That's wow. So we're going to investigate that. We also see something right at 3.1 thousand years ago, and anybody who knows the late Bronze Age, that starts, you go, oh, okay, that sounds interesting. And I'm going to talk about that a little bit later on. Okay. There's also a couple other record events here that you may be noticing. I'm not going to talk about them today because I only have 45 minutes. But there's something at 3.7 thousand years ago, and then another trend that starts around 4.2 thousand years ago. And for archaeologists, 4.2 probably may go, oh yeah, I've heard of that number before. Okay. But for another time. Okay, or you can invite me back next time. Oh, no, maybe 10 months. Okay, so 10 days. Okay, anyway. So let's take a look at some of the other records from this site. Okay, and let's start playing detective, putting the clues together to see what the climate conditions were like during this time. Whoops, I'm going a little bit too fast. So the first one is the oxygen isotopes that we already know. This is warmer sea surface temperatures. Next one is sand percent. When you have more sand, that means stronger currents. And then we have another thing where somebody was actually counting these. Laminations per 10 years. Must have been a graduate student. Anyway, and you can see an increase here, which means like, where the numbers reach around 8 laminations per 10 years. That means it's almost a little cycle every year. Okay, so that means the sea ice is breaking out each year. Again, this is due to stronger current action. That means the sea ice is gone. Okay. So warmer sea surface temperatures, stronger currents. Let's take a look at the simple model from Johnson et al. From 2021. This is a Nature Geoscience paper that was part of, and the model is one mode is weaker winds result in more coastal sea ice, weaker currents. That doesn't sound like us. The other model is stronger winds result in less coastal sea ice. It gets blown out, stronger currents. And this is what the second scenario is, what I think is happening during that oxygen isotope event between 800 and 1400 years ago. So the first thing that Rob Dunbar asked me, he goes, Steve, is this like a local event? And so basically, there's one other core that has high resolution records, and it's from the opposite side of Antarctica, from the Antarctic Peninsula, West Antarctica, Palmer Deep. And this is sea surface temperatures, and look at the correlation here. Okay, there's aliasing in the record. The record is a little bit lower resolution, could be time, but overall, wow, it's an amazing match. And so it looks like the entire Antarctic region, the sea surface temperatures warmed up during this time period. So now the next step is for me to try to show teleconnection from Antarctica all the way to the low latitudes. How do we do this? Well, just about everyone here knows about El Nino, La Nina, the ENSO, okay? We know that. Well, Antarctica doesn't want to be left out with climate phenomena, so we have something called the Southern Annual Mode, or let's call them SAM. And SAM has two phases. A positive one, where we basically have more sea ice in East Antarctica, where the core was, as well as colder temperatures. And then we have a negative SAM, a phase where warm air evects to Antarctica, and the upper 400 meters of the surface waters warm up, and there's less sea ice. And so the first conclusion I want to make is that though that warmer sea surface temperatures is due to a negative SAM phase. I'm going to show you that there are some records to back that up in a moment. But how do we get to the teleconnection? Well, El Nino and La Nina are usually work in phase with SAM. So negative SAM phase is usually occurring with El Nino, almost always. And in fact, if it's the opposite, a La Nina with a negative SAM, they'll basically have they'll basically interfere and weaken each other. So when we talk about negative SAM phase, we're also talking about El Nino at the same time. And so what happens when we have a strong El Nino and a strong negative SAM? This is sea surface temperatures, and you can see right at our site, temperatures are at least about 1 degree warmer than normal. And right at site 1098 on the other side, it's right on the cusp of warmer and cooler. So that's a little bit of, as I talked to Rob Dunbar about this, and he goes, it's right on the cusp. This is just a climate model, but you can see we're right in the deep, thick of the warmer. So yes, so this El Nino will teleconnect with the negative SAM phase, and we're going to get warmer temperatures and less sea ice. Okay, gotcha. So let's take a look at some historical records. Let's look at historical. So here's our little oxygen isotope. Here's our warming of the sea surface temperatures. Here's from southern Chile, looking at percent of this plant. And you can see the blue is negative SAM, correlates pretty good. And they have this little positive SAM in here that correlates pretty nicely with this, and then another negative SAM that correlates with this. Another record from Gomez et al. And then Mason Del Monte from 2004 also shows a similar trend. Negative SAM, little positive SAM, and then a negative SAM, and then another negative SAM. So this is showing that this record is correlating pretty nicely with these global records that are showing the different SAM phases. So you're still, Steve, it's archaeology, okay? So let's get to Central America. So here's our oxygen isotope, again, the warming. These are from records from Lechenet, 2004 from Panama, that was trying to show drought conditions in Panama, and those are going to be controlled by, finally, El Nino. So we have drier conditions here, and they line up very nicely, as well as the increase, this record here, this is basically where it's just getting drier. So we have increased El Nino, and these are all correlating really nicely with the Antarctic records. Wow, okay? So at this point, you're probably thinking, okay, so let's move on. How do we get to Maya? Let's talk about the Maya. Because the Maya was an amazing civilization, complex, but its demise, its collapse in the 9th century, and abandonment of just all the cities were a result of a complex human and environmental interactions. One of the biggest things is deforestation. Large-scale deforestation occurred during the classic Maya. As a matter of fact, who's been to Tikal in Guatemala, okay, or Calakmul, okay, right? When you you climb up these temples that are 200 feet tall, and you look out, and you see this beautiful forest canopy with the little pyramids and temples sticking up. Well, during the height of the Maya, if you went up to the top of the temple, you would see an urban sprawl and then agriculture as far as the eye could see. Yeah, it was completely different. And so the demands of forest clearing for this would result in soil loss. The large population needs fuel for cooking, for making the plaster, so on and so forth. And the deforestation makes droughts worse. Okay, this is basic climatology, where deforestation reduces precipitation by 5 to 15%. And guess what? This deforestation probably is responsible for about 60% of the drying during the Mayan civilization collapse. Okay, so this deforestation enhanced the droughts that were happening all across Central America. The other thing is that they had a huge population. When you go out to Tikal, the largest city is Las Flores. It's maybe 10 to 20,000 people, and then it's jungle. We're talking about hundreds of thousands of people. And in the Yucatan, it's got horrible soil because it's a carbonate platform. It's limestone. It's not going to have beautiful, great minerals coming in from the mountains and stuff. They also were doing slash and burn farming that was going to degrade the soil. The main food sources like corn, low in nutrition. And then even storing it in humid tropical climates is very difficult. So they had a lot of things going against them. And then the final straw was the droughts. As I was showing you, whether it's from Antarctica or the lower latitudes, this is unprecedented. This is one of the worst series of droughts that happened over a millennia. And we can see this in many paleoclimate records, and they correlate very well with the abandonment of the Mayan cities. And so here's a recent paper. This is a great paper from Douglas et al., 2015. He's looked at spelotherms from 2 different caves. And you could see, first of all, spike at 1,400 years, and then a longer, prolonged drought here, okay? And then even a longer drought a little bit later on. And if you correlate this to my Antarctic records, if I was making this up, I could not have drawn it better, okay? I mean, yeah, and so we have a spike, a little bit longer, and then a little bit longer. And so we see this excellent fit here of sea surface warming in Antarctica, getting teleconnected all the way to the droughts that affected the Maya. Wow. And so here is this map. Just to put it in perspective, here's the beginning of the collapse here. Here's the last stela in Tikal, right between this right in here. This is during the first prolonged drought right in here. And you can see, I just love this correlation. The first prolonged sea surface warming takes place at the same time. And so the take-home message I would like to leave with you is that the severe droughts, and hopefully I've convinced you, severe droughts, and this is in the literature, I don't have to convince you, severe droughts contributed to the Mayan collapse. Absolutely. Period. But the events in Antarctica, the climate events, are teleconnecting. They're connected. The whole world atmospheric system is connected. It's beautiful. And it teleconnects to the low latitude climate changes that actually affected the Maya. Okay? So that's the Maya. And that's the data that I have. I would like to now move to another civilization collapse, which is the late Bronze Age. And so in the late Bronze Age, we have severe droughts starting in the 13th century into the 12th century. You can, here's just some of the diagrams. I'm not going to go through them, but it's in the literature. Severe droughts, whether it's archaeology or paleoclimate. And the final straw for the demise of the late Bronze Age in the Mediterranean appears to be this invasion by what's called the Sea People. The Sea People invaded much of the eastern Mediterranean area by water, but also by land in some cases. They came from, we don't know exactly where they came from, probably west of Greece and maybe northwest of here. The archaeologists really don't know. They have some hypotheses. And they basically pillaged one city after another. And the hypothesis is that they came from someplace up here, northwest of here. But what's interesting is that one of the few cities that survived their attacks was the Egyptians. And because of that, we have a pretty nice description of who these Sea People were. And based on the literature, they are not a homogeneous group. They're groups from all over the place. And so the idea is that these seagoing nomads maybe started small, and as they attacked different places, maybe just said, hey, why don't you come with us? Pillaging is fun. And so one of the ideas that has come up is that why did the Sea People come from this area and come down? We know that there was droughts, but there's another hypothesis that there may be a possible connection to the Heckler3 eruption in Iceland. This was one of the largest volcanic events of the last couple thousand years. And one of the ideas is that Sea People may have been fleeing this climate disaster from the northwest after the Heckler3 eruption. However, the timing, and when I was going through the literature, the timing of the eruption is really uncertain. We have ones that correspond to some of my data, 1160 before the Common Era, but there's other ones that are like 1,000 before the Common Era. So, so there is a big controversy with that. So I would like to just share with you how some of my Antarctic records may be picking up signals from these big volcanic events. So let's go back to one of my data sets. Okay, this is a tectonic forams per gram. And when you see these little spikes, this means because tectonic forams, they live in the sea surface and they eat other things. So when you see this big spike, that means there's a lot of them. And that means they had to have a lot of food to eat to reproduce. And so what's happening is we're having this biogenic bloom taking place. And so how can we get a biogenic bloom? Well, this is, and I'm not going to go into the detail of what this is, but this is a sea ice proxy where this is more sea ice and to the left is less sea ice. Basically, in a nutshell, we're basically looking at something called molecular fossils. Okay, little molecular fossils from diatoms. That's as far as geeky as I want to go right now with you guys. But the bottom line is that you could see this huge increase in sea ice, which just must have lasted for decades. And it corresponds with right out, and it's, I'll show you in a couple seconds, this occurs, and then this occurs immediately afterwards at 3.1 thousand years ago, approximately. There's another one that occurs at 2.6, but I don't see any big civilization changes, so let's talk about that another day. Okay? And so basically, when we have a lot of sea ice, the dust starts accumulating on the sea ice. And when the ice melts, all that dust becomes nutrients for the phytoplankton, and they just have this big biogenic bloom. And that's the relationship between sea ice and these biogenic blooms that I see in my planktonic forams. So one thing, after I saw this, I said, okay, let me start correlating it to volcanic events. And so here's age in here, common error. And you could see different ages of volcanic events through time. And you could see this pretty good correlation where we have these biogenic blooms right after these big volcanic events. So, and this is high resolution. This is 6.5 year resolution, so we should be able to pick up most of the signals. The sea ice proxy is about 14 to 20 year resolution, which is still exceptional, by the way. But to actually pick up high resolution changes may not be, but we still see a reasonable correlation. The reds are showing, well, there's no correlation. But there's a reasonable correlation, and that could be because of an aliasing effect, okay? And so let's just do a little, get a little bit closer to this 3.1 event. So we have the sea ice, we have 2 data points showing extensive sea ice lasting for 20 or 30 years. In fact, and I looked it up. I didn't look on a graph. I actually went to the Excel spreadsheet, and this spike here occurs immediately after the sea ice. And so there is a good, reasonable idea that, well, okay, so sea ice builds up, we get a biogenic bloom when it melts. That makes sense. But how does it relate to volcanism? Okay, you see a reasonable good correlation. And could this be the Heckler3 eruption? Could this be the Heckler3 eruption? Well, I don't know. And I just started looking at this. The first part, the Maya, I'm going to start writing up now. The other one but there is a mechanism to correlate volcanic events to the U-1357 records. First of all, right after a big volcanic event, we usually have an El Nino event. That's not good for what I want, because El Nino, less ice, warmer waters, so on and so forth. Not good. However, other papers, and the latest papers from Sun et al. 2017, they say, no, well, the first year is El Nino, but the second and third and fourth years are usually La Nina, or positive sand that's going to cool the surface waters near Antarctica, more sea ice, the whole 9 yards. Okay, so this makes sense. And this provides a mechanism why we can have volcanic events in the northern hemisphere or the equator, and we can still see the signal in Antarctica. Okay? And so, how do these collapses of civilization and climate changes correlate or relate to the bigger picture of climate change? So this is years, this is today 2000, and this is going back 2,000 years. Here's the global temperature anomaly. And you could see the Mayan collapse. I can't even see the climate change. You know, it's a little speck, maybe 1/10 of a degree maybe, okay? What is going on for today? Just for comparison, let's take a look at today. Look over here. This is what we are doing. This is what we have done in the last 140 years. Look at that. This collapses a whole civilization. This is what's happening today. Let's go back further in time, and I'll use another record. This is sea surface temperatures. And actually, I didn't put down the reference. It's from Bova et al. 2021. And we see the Mayan collapse. The sea surface temperatures don't even change. The late Bronze Age, a little bit of a warming perhaps, okay? But we're talking about 1/10 of a degree. What's going on with the sea surface temperatures today? Bang. Look at this. Okay? This is the difference. So the big takeaways here, the climate change that collapsed these ancient civilizations was only on the order of a few tenths of degrees. because most of the changes was like regional, like an El Nino event causing droughts. In contrast, global temperatures have risen over 1 degree, actually it's 1.2 now, and the sea surface temperatures have risen by 0.8 degrees above pre-industrial. And so what I would like to do, so since this talk was about ancient civilizations collapsing because of climate change, maybe we should talk about our civilization and its possible collapse due to climate change. So let me just point out one thing. Climate change is by far described as the most dangerous crisis to confront humanity ever. Period. And this is not what I found on TikTok or Facebook. This is what the best scientists in the world are saying today. And so, and here just a little bit, because we're going to run out of time. This is, the red line is carbon dioxide, the greenhouse gas that's mainly causing the warming. This, the y-axis here is carbon dioxide. Pre-industrial, 280. Today, it's at 415 parts per million and rising fast. Here's the global temperatures in black. Here's the y-axis for temperatures. And you could see that in 2016, we were up to like 1.2 degrees Celsius above pre-industrial. What the United Nations is saying is that we must stay below 1.5 degrees Celsius for global warming, and we're at 1.1, 1.2 degrees above pre-industrial. Okay, we don't have much to go. So you know, it's just so like typical climate skeptic would go, well, it's climate always changing, right? CO2 is always changing. Okay, so this happens to be a CO2 record from an ice core from East Antarctica, and in the x-axis, this is today, and this is in thousands of years. So this is 800,000 years of records of CO2, and you can see that CO2 never gets above 300 parts per million. Where are we today? I already told you. We're at 415 parts per million and rising. So the last time, and you could say, well, climate always changes, right? Climate, the last time that CO2 was this high was 3 million years ago. So what we have done in a little over a century, Mother Nature couldn't do in millions of years. But that's just the tip of the iceberg, no pun. And so, whoops, that just blazed by. So going through some of the thresholds, 450, climate scientists have said, do not go beyond 450 parts per million. We're going to reach that in the next couple of decades. The last time it was that high was 15 million years ago. 15. 550 would be catastrophic. That happened 25 million years ago. So this is what humanity is doing to the atmosphere. We are changing it faster than any time since, whoops, come on, there it goes, since 65 million years ago. And what happened 65 million years ago? Anyone want to shout it out real quick? Dinosaurs, big asteroid hits the Earth, wipes out the dinosaurs. And let me let you on a little secret, guys. It wasn't the dinosaurs' fault that the asteroid hit, okay? And they couldn't do anything about it. In our case, we did it. We did it, okay? But we can also make the changes. And so what Michelle was talking about so eloquently before about all the Glasgow COP26, the new Intergovernmental Panel for Climate Change report that just came out 2 months ago. In the news release, they said it's code red. We're at code red now. Because what they're saying is that we've already warmed the planet to catastrophic levels, but the level of that catastrophe is still up to us. We're already seeing the changes in the atmosphere in our climate now. And it's only going to get worse, because even if we stop CO2 tomorrow, the Earth is going to continue warming for the next couple of decades because there's this thermal inertia. And so some of the things, droughts are increasing. We're watching this, the wildfires, we saw this year. Sea level rise in this century is anything from 3 to 8 feet. I'll talk about that in a second. Freshwater flooding, we saw this with Hurricane Ida. We saw this Hurricane Harvey in Texas. We saw this in Germany. We saw about the 300 people drowning in China in the subway systems. And then, of course, the increasing storm surges. But what's scaring me the most is that this is going to result in food shortages, and large areas are going to become unlivable because of either sea level rise or just becoming too hot. And this is in the report. And also, actually, and it's going to result in mass migration on the order of millions to tens of millions of people. And actually, that's a little bit wrong. I underestimated. There was a World Bank report that came out that said by 2050, that's 28 years from now, it could be on the order of hundreds of millions. Hundreds of millions. And then a paper just came out by Zhu et al. 2021 that said by 2070, it could be hundreds of millions to billions. And so it's really, and this is, so there's no going back. But we have to act now. And right now what's happening in Glasgow is our best last chance. And so you should be watching the news, calling up a congressperson, so on and so forth. And so what does the climate scenario show? So this is showing years in the x-axis. This is how much CO2 is being emitted. And this is just different models. Like if country X does this and country Y does that, and so on and so forth, and other variables. And the business as usual, we're not quite a business as usual anymore, thank goodness, but that would be beyond catastrophic. The problem is that we're still in really bad futures because even with the Paris Accord, we're heading for a 2 to 3 degree warming, and we're supposed to be staying at 1.5 degrees. The only solution is to drastically cut emissions within the next 8 years by 2030, and so we can start bringing down the CO2 levels. That's the only safe option left. And so currently, we're following the scenario for the RCP6, which is right up in here. That's 2 to 3.5 degrees warming, and the Paris Accord is following the same thing. We need to do a lot more, a lot more. And so this came out last year. Okay, this was IPCC report that talked about on how the importance of staying within 1.5 degrees of global warming from pre-industrial. And so this is some of the different things. Warm water corals, it's already bad. Anybody who does snorkeling or scuba diving, okay? We've seen the coral bleaching all around the world. It's catastrophic, okay? The Arctic region, even at 1 degree was bad. Red is really bad, and catastrophic is purple. And you can see by the time we reach 2, Arctic region, it'll be basically effectively ice-free by 2034. That's the latest, that's 12 years from now. Coastal flooding is going to be catastrophic, fluvial flooding, so on and so forth. This is bad. And so since I don't have much more time, I'm just going to show you.
I'm not shortening. This is such an important talk. Please.
Oh, well, let me include some more slides then. No, but like, I got a whole bunch more. You know, and so, don't get me started. I'm a New Yorker. And so, but I just want to point out two topics that I think will kind of shock you. India is running out of water. So is parts of China, so is parts of the Southwest United States. So, but India, it's got 1.4 billion people. And so, and actually, Annie and I, we went to India about 10 years ago through Queens College, and as basically ambassadors, and when I gave some talks there, and I talked to environmental scientists, and back then, they were almost in tears. They were so upset over what was going to happen in India. So they knew this years ago. The scientists always know. As a matter of fact, you know, at the beginning of any big disaster movie, there's always a scientist who's going, "Excuse me," you know. And so in India, 600 million people face extreme water stress. By 2030, 8 years from now, we're talking about half of the water that will be needed is going to be available. And then even worse, 21 of the major cities, that's 10% of the population. And if we were talking about Albania, who cares, right? Because it's a tiny country. India, 10%, that's 140 million people. And these major cities are going to exhaust the groundwater supplies within the next 8 years. Okay, and we're doing this in the Southwest also. Because of fracking in Texas, they drain the groundwater, and so there's towns in Texas where they have to truck the water in all the time. It's not going to be on the news because it's not popular, but that's what's happening. So this is catastrophic. Okay, And so the last little thing I just want to mention is sea level rise. And as estimated, sea level rise in this century is 2.5 to 8 feet. I think it's close to 6 to 9 feet. Based on, for example, Decanter and Pollard from 2015, they said it was not feet, a couple of feet, it's going to be a couple of meters of sea level rise. I co-authored a few papers with him, in fact, so I know him. James Hansen, the guy from GISS, who went to Congress 30-something years ago and talked about climate change. He wrote an article, and he said it ain't going to be 1 or 2 feet, it's going to be a couple of meters, 2 to 3 meters of sea level rise. So this is what sea level would do with a 7-foot sea level rise to Coney Island. There goes the cyclone. Rockaway Beach, and I could show you that all around the Gulf Coast, East Coast, Manhattan. This is what we're facing in the next, in our century, okay? And actually in the upcoming decades. And so let's talk about it. What can we do? Well, first of all, I don't want to be mean to our newscasters because we just love our little CNN or whatever you like, but they're not doing a good job. I just showed you some stuff, and I could have shown you a lot more of what the scientists knows, and we're weeping over this, and it's not on CNN. It's not even on MSNBC. They're not giving us all the information. So you have to go to the IPCC report. It's easy. You don't have to read all 500 pages, okay? There's nice little synopsis, and it's maybe 10 pages with graphs. The Guardian newspaper from the UK, they have climate every single day. And right now, because of the COP26 in Glasgow, they have 3 to 5 articles every single day about climate change. Okay, we don't see that. And then, of course, you can go to climate change organizations like 350.org, Climate Reality. But once you get educated and you know what's going on, talk to your elected officials. Go to your TV and say, hey, why are you not talking about this? And then, once you're educated, win the conversation. Don't let denial go unchallenged, because that person's going to vote for the other candidate then, okay? And tell your elected officials, and don't give up. There is a lot of great will. There's so many people out there in the world that are fighting this and being successful. In fact, the bill that's in Congress right now, I don't want to be political, but I'm just a scientist. I'm just going to give you the bloody facts. The bill that's in Congress, the Build Back Better, there's something like over $500 billion for climate change. This will take us from, the previous administration that said windmills cause cancer and climate change is a hoax, and he pulled out of the Climate Paris Accord. We're going to go from pariahs to world leaders for climate change. This needs to be passed. So laws are much more important than going, oh, I don't have an electric car yet. Don't worry about it. I can't afford it either. I'm just a college professor. And so, but we got to start acting now, okay? And so, in summary, let me finish up now. We are learning that the global climate signals interconnect from the high latitudes to the low latitudes, from Antarctica all the way to the equator, and these are all teleconnected. There's teleconnections throughout. The climate events seen in the low latitudes and Antarctic records can be ascribed through ENSO and SAM phenomena. I kept it a little easy tonight. There's IPO and AOM and IOD and everything, but and I'm not making it up. But these are the two biggest climate phenomena in Antarctica and at the low latitudes. However, even as these climate events were catastrophic for the past, for these past civilizations, they just pale in comparison. And you saw what I just showed on the climate emergency our present-day civilization is facing in the coming decades. Okay, and only immediate, drastic action to end the release of greenhouse gases will diminish the climate catastrophe that awaits humanity in the coming decades. And with